active or less active form. Regulation of asper- as- aspartate transcarbamoylase. A specific example of a regulatory enzyme is aspartate ATAcase. This enzyme catalyzes a regulatory step early in the biosynthesis of pyrimidine nucleotides. In this reaction, carbonyl phosphate and aspartate combine to form N-carbonyl aspartate. Carbonyl phosphate, aspartate, N-carbamoylase. Regulation of aspartate 2. ATcase has 12 polypeptide chains organized into 6 catalytic organized as 2 trimeric complexes and 6 regulatory organized as 3 dimeric complexes subunits. The regulatory subunits have binding sites for ATP and CTP, which functions are positive and negative regulators. Respectively, CTP is one of the end products of the pyrimidine nucleotide biosynthetic pathway, and negative regulation by CTP serves to limit ATcase activity under conditions cellular metabolism is robust. The cell is growing and additional pyrimidine nucleotides may be needed to support RNA transcription and DNA replication as shown in the diagram. The binding of the negative modulator CTP to the regularity subunits produce large change in enzyme conformation and converts the complex to the less active state T state. Kinetic properties of regulatory enzyme 1. Allosteric enzymes show relationship between V0 and S that differ from kinetics. They do exhibit saturation with the substrate when concentration of substrate is sufficient high, but allosteric enzymes plot of V0 versus S usually produce a sigmoid saturation curve rather than the hyperbolic curve, typically of non-regulatory enzymes. On the sigmoid saturation curve, a value of S at which the V0 is half maximal can be identified, but cannot be referred to as the Km because the enzyme do not follow the hyperbolic relationship. Instead of the symbol is often used to represent the substrate concentration, giving half maximal velocity for the reaction catalyzed by an allosteric enzyme. Sigmoid kinetic behavior generally reflects cooperative interaction between multiple protein subunits. Changes in the structure of one unit are translated into structural changes in adjacent subunits due to changes in non-covalent interactions at the interfaces between subunits. Sigmoid kinetic behavior is explained by the concerted and sequential models for subunit interactions. Kinetic properties of regulatory enzymes 2. Substrate activity curves for representative allosteric enzymes that show complex responses to their modulators as shown in the figure. In panel A, the sigmoid curve is for a homotropic enzyme for which the substrate also serves as a positive modulator. This curve black resembles the oxygen saturation curve for hemoglobin. The sigmoidal curve is a hybrid curve in which the enzyme is present primarily in the relatively inactive T state at low substrate concentration and primarily in the more active R state at high substrate concentration. The curves for pure T and R states are plotted separately in color. ATKs exhibits a kinetic pattern similar to this in response to the concentrations of its substrates, aspartate and carbamyl phosphate. Kinetic properties of regulatory enzymes 3. In panel 2, in panel B of Fig 631 curves are plotted showing the effects of several different concentration of a heterotropic positive modulator positive and a heterotropic negative modulator negative on an allosteric enzyme in which case 0.5 is altered without a change in Vmax. The central curve shows the substrate activity relationship in the absence of modulators. The curve shows are similar for ATKs in the presence of the negative modulator CTP and the positive modulator ATP. Kinetic properties of regulatory enzyme 4. In panel of the figure 6.34 curves are plotted showing the effects of modulators and the change Vmax without significantly change K0.5. This is less common type of elastic regulation and it is not observed for